Hi guys, this is Dr. G here, and in this video we will talk about Brønsted-Lowry definition for acids and bases. So according to Brønsted-Lowry definition, acids are known as chemical species that are capable of donating protons. So let's consider Ha as a generic acid, okay? So if it is an acid, you have to have a donatable proton. So this hydrogen right here, let's consider that as a donatable proton, and then it is donating it into water, forming hydronium ions, okay, hydronium ions, and then A minus. Of course, if Ha is a strong acid, okay, you will have a single headed arrow, okay, but in this reaction that I have drawn, you have a reversible arrow, which means Ha is actually a weak acid, okay, it is a weak acid. So Ha is going to be your acid, okay, and then A minus is going to be your conjugate base. Okay, so in this weak acid called Ha, the conjugate base is going to be A minus. Okay, so similarly, according to Brønsted-Lowry definition, bases are chemical species that can accept protons. Okay, that can accept protons. So in here, let's consider B as our base. Okay, so in this chemical reaction, what happens is that the lone pair on B will be accepting a proton from water, forming Ha. Excuse me, let me change the color. So you are accepting a proton from water, so you will be Hb, okay, and then you will also have OH minus in the reaction medium. Okay, so in here B is your base, B is going to be your base, and Hb is going to be what? It is not acid, but it is going to be conjugate acid. So this is how you define acids and bases in Brønsted-Lowry definition. Acids are capable of donating protons, okay, forming a conjugate base. Bases are capable of accepting protons, forming a conjugate acid. So it is very important that you guys remember this definition. All right, so next thing that we are going to talk about is the acidity constant, which is also known as Ka. Okay, the important thing about Ka is that acidity constant is important in measuring the acid strength. Okay, so if you have an acid, you want to know whether it's a strong acid or a weak acid, or how strong your acid is, right? So Ka will basically give you a measurement of the strength of your acid. Okay, so let's take our Ha acidic reaction. So for this acidic reaction, you can write an equilibrium constant. So the product concentrations will be on top. So A minus concentration, the square bracket means concentration, times H3O plus concentration divided by product concentration. So Ha and water concentration. Here's the thing, at constant temperatures, okay, at constant temperatures, water concentration is actually a constant, right? So rather than writing the concentration of water, we can rearrange this equilibrium constant, okay, where you will multiply the concentration of water from the equilibrium constant. So you get Ka, okay, Ka is equal to A minus concentration, which is our conjugate base, and then H3O plus concentration divided by Ha. Once again, guys, when we are deriving the equation for Ka, we multiply the equilibrium constant by the concentration of water. So you will no longer have the concentration of water, which is a constant, and instead you get Ka, which we call acidic constant. So basically, acidic constant will give you a measurement of how strong the acid is. Okay, it will basically tell you how strong the acid is. So as you can see, okay, in this equation, Ka is proportional to H3O plus concentration. Am I correct? Ka is proportional to H3O plus concentration, which means H plus is basically how many protons you have in water, right? So basically, if you have more protons, the mixture is acidic, right? So if you have high concentrations of H3O plus, Ka is going to be high, and vice versa. Okay, so since H3O plus concentration and Ka is proportional, so if Ka is high, okay, if Ka is high, the acid is capable of generating more H3O plus or protonium ions. Okay, more protonium ions. And of course, if Ka is high, acid is stronger. Okay, if Ka is high, acid is stronger. But here's the thing, this Ka could have a huge range. It could start with lower 10 to the power negative values or even positive values sometimes, and then it might go to very low 10 to the power values. Okay, so Ka has a huge range when it comes to different acids and bases. Okay, so rather than using Ka, it is more convenient to basically use the log value of Ka. So basically what we commonly use as compared to Ka is pKa. Okay, so you are familiar with this P from your previous chemistry lessons. Whenever we use a lowercase p, we know that we are using the minus log value of that particular constant. So in here we have Ka. Okay, so in here what we do is we are taking the logarithmic value, not only just logarithmic, we are using the negative log value of Ka. Okay, by doing that, we are basically contracting the scale for Ka, and not only that, we are inversing the Ka scale. Okay, we are basically flipping the Ka scale. So in the beginning, you know that Ka, if Ka is high, the acid is strong, right? But now, since we are inverting the Ka scale by using pKa, so stronger acids, of course, has a high Ka but smaller pKa. Okay, strong acids have a smaller pKa. That is important to remember. Okay, and weak acids have a larger pKa. Okay, so I'm going to highlight this. This is important to remember. Okay, so stronger acids have a smaller pKa. Weak acids have a larger pKa. That is important to remember. All right. So with that, let's get some examples. Let's go and take a look at some of the general examples. Okay. All right. So this table is actually directly from your organic chemistry textbook by John McMurray. Okay. So in here, as you can see, I have given you certain weak acids. Okay, certain weak acid or sometimes even strong acids like HCl, and then also there are pKa values. Okay, so as you can see, HCl is a very strong acid, and what happens to the pKa? It is negative, so it is very small. So stronger the acid, smaller the pKa. But if you have a weak acid like water or even something like alcohol, okay, they have very large pKa values. So if you have a larger pKa value, the acid is weaker. If you have a stronger acid, the pKa value is going to be smaller. All right. So with that, let's talk about the relationship between pK and pKb. Okay, let's talk about pKa and pKb. We already know what is pKa. pKa is actually minus log of Ka, minus log of our acidity constant. So we already know what is pKa, which is minus log of our acidity constant Ka. Okay, so What is pKb? Okay, we have never talked about pKb in this particular video. So pKb should be, I mean, it has a p, so it should be minus log of the constant called kb. Okay, kb. So kb is actually known as basicity constant. Kb is known as basicity constant. So here's the thing, where does this kb comes from? We only had an acid, right? So for an acid dissociation, we can write uh, Ka. Of course, for an acid dissociation, we can write Ka. But remember, if your acid is a weak acid, especially if your acid is a weak acid, where you are using a reversible arrow, that means it is a weak acid, right? So if your acid is a weak acid, the conjugate base can also go back and regenerate Ha. And this backward reaction actually could generate protons. So let's take a look at it. So we already know how to write Ka, right? Ka is equal to A minus concentration, H3O plus concentration, divided by Ha concentration. Once again, Ka is proportional to your conjugate base concentration and H3O plus concentration. So stronger acids are more powerful because you have more concentration of H3O plus. So stronger acids have high Ka values. And then for the conjugate base that you have generated from the previous reaction, it can also go back and produce the acid. Okay, so this reaction is actually a basic reaction. Why? Because you are forming OH minus ions. So this reaction is a basic reaction. So conjugate bases reacting with water to give you an acid and a OH minus is a basic reaction. So for this reaction, rather than writing Ka, you will write Kb, because Ka is for acids and this reaction is a basic reaction. So for Kb, similar to Ka, you can write the product concentrations, which is Ha concentration times OH minus concentration divided by A minus concentration, which is your reactant. Okay, so this is Ka and Kb for the same acid and the conjugate base pair. All right, so now what we do is we can multiply, we can multiply Ka from Kb. If you multiply Ka from Kb, let's try to multiply Ka from Kb. So Ka is H3O plus concentration times A minus concentration. I would recommend that you guys do this with me so that you can practice on how to use these terms. So this is your Ka and then multiplied by Kb, so it will be OH minus concentration, Ha concentration, and A minus concentration, conjugate base concentration, right? So in here, as you can see, Ha to Ha will cancel out and A minus to A minus will cancel out. So all you have left when you multiply Ka and Kb is H3O plus concentration and OH minus concentration. We are actually familiar with this relationship, right? H3O plus concentration times OH minus sign concentration, that is called Kw. Okay, or in other words, ion product of water. So basically, when you multiply Ka and Kb, when you multiply Ka from Kb, you get Kw. Okay, Kw. And this Kw is actually equal to 10 to the power minus 14, 10 to the power minus 14 at 25 degrees Celsius. Okay, from our previous knowledge, we know that Ka multiplied by Kb is equal to Kw, which is 10 to the power minus 14 at 25 degrees. So this is the relationship between Ka and Kb. Why is this relationship important? Okay, why is this relationship important? So let's take the pKa. I mean, let's multiply this whole equation, or let's take the minus log for this whole equation. If you do that, you get pKa plus pKb equals 14 at 25 degrees Celsius. Okay, at 25 degrees Celsius, pKa plus pKb equals 14. Okay, or you can say pKw, which is 14. Okay, so according to this equation, the sum of pKa and pKb is a constant, at constant temperatures. Okay, once again, let me tell you this again. So the sum of pKa and pKb is a constant at constant temperatures. So that is an important discovery. So let's highlight it. This discovery is important. So at constant temperatures, pKa and pKb sum is a constant, which means for a acid and a conjugate base pair, the pKa and pKb sum is a constant, which means if you have a stronger acid, you have a weaker conjugate base. Okay, you have a weaker conjugate base, or vice versa. If you have a weaker acid, you have a stronger conjugate base. Okay, let's use some numbers. Let's say you have an acid called HA and HB. Okay, so let's say you have two acids. Let's say you have an acid called HA, you have an acid called HB. They are both acids. And for HA, let's say the pKa value is 4. Okay, for HB, let's say pKa is 8. Okay, is 8. So let me ask you this question first. Which acid is strong? Is it HA or HB? Okay, which one is strong as compared to the other, of course. So you look at the pKa value. Okay, you look at the pKa value, and the lower pKa means it is stronger. Okay, so stronger acid will have a lower pKa. So HA is the strong acid, right? Strong acid. So let me ask you this question. What will be the pKb for A minus? What will be the pKb for A minus? It will be 14 minus 4, which is 10. Okay, and what will be the pKb for B minus? It will be 14 minus 8, which is 6. Okay, so when you take the conjugate bases, stronger conjugate base is B minus. Okay, so B minus is stronger. Okay, so when it comes to acid, acid HA was the stronger one. Okay, but when it comes to conjugate bases, B minus is the stronger base, which means if an acid has a stronger pKa, if an acid has a stronger pKa, that conjugate base will have a weaker pKb. So basically, for stronger acids, they have weaker conjugate bases. So in conclusion, we can say that stronger acids have weaker conjugate bases and vice versa. That means weaker acids will have stronger conjugate bases. So it is very important that you guys remember this conclusion. Okay, stronger acids have weaker conjugate bases and vice versa. All right, so let's go back to your textbook example. Okay, let's go back to your textbook example and let's take a look at some example acids and bases. So I'm going to show you the same table from your textbook. Okay, so as you know, when you have a smaller pKa, that's a weaker acid. Smaller pKa means what? You have a a larger pKb, right? You have a larger pKb, so the conjugate base will be stronger. Okay, so weaker acids have stronger bases, and stronger acids have weaker conjugate bases. Do you understand that now? Since pKa plus pKb is a constant, or let's say 14 at 25 degrees Celsius, okay, stronger acids have weaker conjugate bases, and then weaker acids have stronger conjugate bases. All right, that is important to remember, and actually it is very important to remember. All right, so in this slide I have a sample problem that is related to pKa values. Okay, so let's see if you could do this example without my help. All right, so you might want to pause the video and try this. So in this example, you have two amino acids, okay, phenylalanine and tryptophan. You have phenylalanine and tryptophan. So those are the two acids you have. You have phenylalanine with a pKa of 1.83, and then you have tryptophan with pKa of 2.83. Okay, so it is asking which acid is stronger. So you look at pKa values, right? pKa values. So according to pKa values, the smaller pKa values are the acids that contains strong acids, right? So it's smaller the pKa value, stronger the acid. So this is stronger. Right, so according to this example, phenylalanine has a lower pKa value, which means it is the stronger acid. It is the stronger acid than tryptophan. All right, so here is the answer. And let's take a look at some other uses for these acidity constant or pKa values. Okay, log scale of acidity constant. So one of the very important uses for these pKa values is the use of pKa values in predicting the feasibility of a reaction. So if you want to predict whether a given acid-base reaction is going to take place, you can obviously take a look at the pKa values. Okay, so if the difference in the two pKa values are significant, okay, and also if you are making a weaker conjugate acid or acid from a strong acid, that reaction will take place. Okay, that reaction will take place. So of course, when predicting acid-base reactions, you look at the two pKa values, and then you can basically predict the feasibility of a reaction. So here is an example. I want you to pause the video, and then using the pKa values that I have shown you in a previous table, see if you could solve this problem. So if you don't remember the pKa values, let me give you the pKa values for HCN, which is 9.31. This is the pKa for HCN. And then for acetic acid, pKa value is 4.76. Okay, so using these pKa values, let's see if you could predict the feasibility of this reaction, or will the following reaction take place to a significant extent by using the pKa values. So you might want to pause the video and see if you could do this one. All right, so here's the thing. Okay, so let's take a look at the pKa values. Tell me which is the strong acid. Acetic is the strong acid, right? Acetic is the strong acid. Why acidic is the strong acid? Exactly, because acetic has a smaller pKa value. Smaller pKa value means it's the stronger value, strong acid. And in here, HCN is going to be your weaker acid. So you are basically starting with a weaker acid. Okay, so you are starting with a weaker acid, and then you end with a strong acid. Can you do that? You are starting with a weak acid and you are ending up with a strong acid. No, that is not feasible. Okay, that is not feasible. So since acetic acid is stronger than HCN, this reaction will not take place. Okay, since acetic acid is stronger than HCN, this reaction will not take place, because you should start from a strong acid and then produce a weak acid. Okay, but in here you are starting with a weak acid and then produce a strong acid. That is not possible. All right, so this reaction will not take place. So here's the solution. Okay, you can pause the video and write the answer. With that, I'm going to conclude this video. So please feel free to ask any questions. Okay, you can email me or you can schedule a Zoom meeting, but let me know if you have any questions. Okay, and you guys have a good one. Take care.